Afternoon.
Afternoon, sir.
Good afternoon, sir. Good afternoon, sir. Good afternoon, sir. Good afternoon, sir.
Okay, so last time we were talking about weak induction principle, right? And weak induction principle. So uh, prove that statement is true for n is equal to 1. Then prove that statement is true for, assume that statement is true for k, and then from that you can prove for k plus 1. Then the statement is true for all. And last time we proved the general version of De Morgan's law. Right. So general version is if you have n number of sets and their union of complements is same as intersection of complements. Same is for complement of intersection is union of complements. So that is what we discussed last time, right? So last time we discussed this. Now we'll see some more problems, and then we'll see the general version of De Morgan's laws. Okay, so now can you see the new screen?
Yes, sir.
Okay.
Yes, sir.
So weak induction and or it is also called as first induction principle. Right? So these are main steps. Now let us try to see one more problem. So okay, well, prove that if x is greater than -1, then 1 plus x raised to n greater equal 1 plus nx for all natural numbers n. Right, so this is a problem. Now you choose any x, and if once it is a greater than -1, then 1 plus x raised to n is greater equal 1 plus nx for all natural numbers. This is our statement. So this inequality is called as Bernoulli's inequality. So Bernoulli's inequality. Okay, so problem is clear. Once you choose any any real number x greater than -1 on this side of -1, then 1 plus x raised to n is greater equal 1 plus nx. So what is first step? So step 1. So we shall use induction because we want to prove that it is true for all natural numbers. And what is x? You fix. Now at a moment x is fixed, right? You choose any x once it is greater than -1. So x is fixed. And for every such x, this is true. So therefore, we want to prove it is true for all natural numbers. So we should use induction. So what is the first step? Prove for n is equal to 1. Right. So if n is equal to 1, what is the left hand side of statement? So 1 plus x raised to n.
X raised to 1.
So it is simply 1 plus x, right? And
Yes.
it is same as 1 plus x, right? So same thing, and 1 plus 1 times x. But n is 1 in this case, so 1 plus nx. It is equal, exactly equal, and there is no harm in saying that 1 plus
Not audible, sir.
nx for
Your
n
voice is
is
not
equal
audible.
to voice is not clear.
Yes,
No,
sir.
sir.
Yes. Can you hear me? Can
No,
you
sir.
hear me?
Yes, sir. Yes.
Yes. Can you hear me? Is it clear now?
Yes,
Yes, sir.
sir.
Yes. Yes, sir.
Yes, sir. Yes, sir.
Okay, fine. Now the statement is true for n is equal to 1, right? Because if you choose n is equal to 1, certainly the left hand side and right hand sides are equal. Equal means we can say that greater equal. When I say greater equal means either greater or equal. So if one of them is true, then I can say it is greater equal. So second step, induction hypothesis. So second step is induction hypothesis. So what is induction hypothesis? Assume that the
Assuming that
statement
any statement is true for n is equals to k.
statement holds for n is equal to k. That is 1 plus x raised to k is greater equal 1 plus kx. This we are assuming. And this k is a particular k. Now we have selected some which is greater equal 1. Right, and this is a particular k, and from this can we prove for next, right? So the inductive step. What is inductive step? Prove for k n is
Is
equal.
equals to k plus 1.
So prove for n is equal to k plus 1 using induction hypothesis, right? So you have to use second step to prove for n is equal to k plus 1. Fine, and therefore, if this is our aim, so start with, so therefore consider. Let us start with 1 plus x raised to k plus 1, and our final aim will be it is greater equal 1 plus k plus 1 times x. That will be our final expectation, right? So this is 1 plus x raised to k times 1 plus x. So please keep your mic off because somebody has kept mic on, so it creates noise. Okay, now by induction hypothesis, sorry,
Sir, audible, sir.
can you hear now?
Yes, sir.
Okay.
Yes, sir.
Sir, your
So
screen is not visible.
it might be happen. Can you? Is it the same problem with all others?
No, sir.
No, sir.
No, sir.
It's visible.
Others
No, sir.
can see. It may be
No, sir.
the due to internet connectivity. It happens sometimes. So don't get panic, right? Okay. So 1 plus x raised to k into 1 plus x. Now this is a product of two expressions or two terms or two numbers you can say. Right. Now if I replace 1 plus x raised to k by 1 plus kx, right, I am replacing first bracket here by 1 plus kx and second as it is 1 plus x. Now which expression is bigger if you compare this expression and this second expression? So which expression is bigger, right?
First one.
So first
First
one is
one.
bigger
First.
because by
Yes.
induction hypothesis, 1 plus x raised to k is greater equal 1 plus kx, and therefore certainly this bracket is bigger than this. Right, now expand the second expression, that is multiply 1 plus x plus kx plus kx square. If I multiply these two brackets in the last expression, so I get this. But 1 plus x plus kx, I can combine these two terms so that I will get 1 plus k times x plus kx square. So the last expression is involves three terms, and in this last term is positive. Suppose I delete this term, what is the resulting quantity? Suppose I delete the last term in the last expression, then I will get this, right? Suppose I delete the quantity last term. So what is the result? Result will be this, right? And I am deleting something positive quantity, right? And therefore, if I am deleting positive quantity, then resulting amount will be smaller, right? So resulting amount will be smaller. So okay, so if I delete last quantity, is it clear? So 1 plus k times x plus kx square, this is my expression, and in that expression last term is kx square. I am deleting this quantity, the result remains this. Okay, so now compare this and this expression, which is bigger. So certainly this is big, right? This is bigger because in the second expression, last expression, some quantity is deleted, which is positive quantity because it is kx square, right? And so ultimately what we started with, thus we started with 1
So why did
plus,
you deleted that quantity?
see, if I delete, then resulting amount is smaller. Is it true or false? Right?
Yes.
Yes,
Right.
sir.
So whatever I am doing is not wrong. But if I am doing which is not wrong, that will leads us to the our expected answer. Is it clear? Because I want to achieve something. That's why I am doing this. And
Yes.
whatever I am doing, I am not violating any rule of mathematics, right? Whatever deleting, it is according to the rules of mathematics, right? If I am deleting, then I am saying that it is smaller quantity. Okay, so ultimately I started with 1 plus x raised to k plus 1, and at the end where I reached, so this amount is, I reached to the some smaller amount, which is 1 plus k times x, and this is what we were expecting, right? This is what we were expecting, ki 1 plus x raised to k plus 1 is greater equal 1 plus k plus 1 times x, right? So please keep your mic off immediately. Right. So hence the result or inequality is true for n is equal to k plus 1. This is what we were expecting. What we were expecting, 1 plus x raised to k plus 1 is greater equal 1 plus k plus 1 times n. That is what we obtained. Right. So we started with this amount and we simplified it. We are able to simplify it so that we can get the smaller amount, which is 1 plus k plus 1 times x. So by induction, hence by induction, okay, here one more thing you should remember here, that x is where we use the assumption that x is greater than minus 1. X is greater than minus 1, where we use this assumption, right? If we are using we are making some assumptions, or we are considering something that must be used somewhere, otherwise we do not we should not make unnecessary assumptions. So basically, if a is greater than b and c is positive, then ac is greater than bc. This is a very important property of real numbers, right? Do you agree with this? If a is greater than b, c is positive, and if you multiply by c on both sides, then ac is greater than bc. This is what the property of real numbers. But if c is negative, then it may not be the inequality may not be right. So for example, 5 is greater than 3 and c is equal to suppose minus 1, and if I multiply by minus 1 on both sides, what will happen? So what will happen? Minus 1 times
Signs
5.
will be reversed.
So minus 1 times 3, which is minus 5 and minus 3. In that case, inequality is reverse. Here it was greater. Now if you multiply by negative number, the inequality becomes opposite. But if C is positive, then this inequality greater than remains greater than, right? If C is positive. So where we use this property? Where we use? Here we use this property in this step. 1 plus x raised to k and 1 plus kx. By induction hypothesis, what was our, just compare with this, what was our a? Suppose a is 1 plus x raised to k and b is 1 plus kx, right? Then by induction hypothesis, a is greater than b. That means 1 plus x raised to k is greater than 1 plus kx. And what is c now? 1 plus x. If I multiply by c on both sides, then what I will get? Right, this is a, this is b, and a is greater than b by induction hypothesis. And if I multiply by c, c is 1 plus x, 1 plus x, this inequality remains greater or equal, but under the assumption that 1 plus x is positive. But what is the guarantee that 1 plus x is positive? So that if I multiply by 1 plus x on both sides, the greater than remains greater than. What is the guarantee that 1 plus x is positive? So here, that's why we made this assumption. 1 x is greater than minus 1. Therefore, 1 plus x is greater than 0. Is it clear? Right. In general, this will not be true. But we are sure that 1 plus x is positive. That's why this remains greater. And why we are sure? Because we have already made the assumption that x is greater than minus 1. Okay, so therefore, that makes sense now. Otherwise it will not be the, it will be the wrong step otherwise, if we are not sure ki 1 plus x is positive, but we are sure now. Okay, fine. And therefore now proof is complete. When proof is complete, if you understand each and every step, meaning of each and every step, logic behind each and every step, so there is no confusion in any step, then proof is clear now. Fine. So hence by induction, 1 plus x raised to n is greater equal 1 plus nx for all n, and x greater than minus 1. If x greater than minus 1, then this is true for all natural numbers. Fine, this is what we proved just now. So there are many statements in mathematics which we can, in which induction is useful to prove such statements. So for example, prove that 3 raised to n is greater than 3 raised to n is greater than n square. So prove that 3 raised to n is greater than n square for all natural numbers. Right. So we shall of course the statement is about natural numbers. We want to prove that it is true for all natural numbers. So we shall use induction. Right. So step 1, prove for n is equal to 1. Now if n is equal to 1, then what is 3 raised to n? 3 raised to n is 3 raised to 1. And what is n square? N square is 1 square, 1, and certainly it is greater than, right? Therefore 3 raised to n is greater than n square. So true for n is equal to 1. But in this particular problem, we need to check for n is equal to 2. That we'll see later on why we need n is equal to 2 also. If n is equal to 2, then what is what is 3 raised to 2? 3 raised to 2 is 9.
9.
And is greater than 4, which is 2 raised to 2. That is 2 raised to n in this case. right? So the result is true for n is equal to 2 also. So true for n is equal to 1 as well as 2. Now step 2, induction hypothesis. Assume that the statement is true for n is equal to k. And what is not my k now? I am assuming is k is greater than or equal to 2, right? Because due to some next step we can understand this. That is 3 raised to k is greater than k raised to 2, right? So that we are assuming. So step 3. So inductive step. So to prove in step 3 what we want. So what we want to prove for n is equal to k plus 1. That is we want what we want 3 raised to k plus 1 is greater than k plus 1 raised to 2. This we want. This is expectation, right? This is not a proof. We have not proved for k plus 1. So therefore let us consider 3 raised to k plus 1. Start with this and try to get that key this is greater than k plus 1 square. Let us start with this. But this is 3 raised to k times 3. We can split this k plus 1, 3 raised to k plus 1 in this way. This is the usual property of exponents. No, not difficult at all. Okay, but by induction hypothesis, 3 raised to k is bigger than k square. 3 raised to k is greater than k square. So if I replace 3 raised to k by k square and I keep 3 as it is, so which amount is bigger? So certainly 3 raised to k is bigger. 3 is positive number, and by induction hypothesis this number is greater than this, and multiply by 3 which is positive, the inequality remains same, right? So that means this is 3 times k square. But 3 times k square means it is k square plus k square plus k square. That means 3 times k square. Right. Now I will k square as it is, and I will replace this k square by 2k, and I will replace k by 1. Right. So what I am doing here? Recall this. So k square, and k square means it is k plus k into k, and I have another number k plus 1. Which number is bigger, k square or k plus 1? Which is bigger?
K square.
K
K
square.
square.
Very good, because my k is greater equal to, right, and square is always greater than k plus 1, certainly. Therefore if you compare these two expressions, so try to compare these two expressions. So please keep your mic off immediately. So compare these two expressions, k square as it is, no doubt, right? Suppose I have three boxes containing equal weight, right? This box contains 5 kg mangoes, this box contains 5 kg mangoes, and this box contains 5 kg mangoes. Now what I will do, in first box I will keep as it is 5 kg mangoes. From second box I will remove some amount of mangoes, so second box now contains less amount, it is 2k. Okay, k I wanted to have now k plus k. So if I compare k square and k plus k, which is bigger?
K square.
Which
K square.
certainly
K
k
square.
square is bigger. So because our k is greater than or equal to 2, so if I compare k square and 2k, then k square is bigger. Now k square and 1, which is bigger? K square
Sir,
is bigger.
but if k is equal to 1,
Okay, so you are saying k is equal to 1, but why I am assuming that my k is greater equal to. Is it clear?
okay,
I am
sir.
not worried about k is equal to 1. I have already proved for k is equal to 1. So at this moment, I am not worried about k is equal to 1. I am worried about
And
the
sir,
larger,
if
greater
k
than.
is equals to 2,
K is equal to 2, then
uh,
k is
2 into 2 also 4 and 2 plus 2 also 4.
so these amounts may be same, but certainly this amount is larger, k square is greater than 1, right? K square is greater than 1 or not? K
Yes,
square
but
is
but
greater
k
than 1.
square is not greater than k plus k. It is equal. Na?
That's fine. No, that is not an issue for me right now, right? Okay, let me tell you. Suppose I have 3 boxes. This box contains 5 kg mango, 5 kg mangoes, 5 kg mangoes. Okay, suppose I keep these 2 boxes as it is, 5 kg, 5 kg. And suppose I reduce the mangoes from this, and this contains only 3 kgs mango. So which amount is larger? This total amount is larger than this. Am I right? Suppose I keep first
Yes.
box as it is 5 kgs mangoes, second box as it is 5 kgs mangoes, and from third box I remove some amount of mangoes. The 2 kgs I removed. What remains? Only 3 kgs. And then what is the total amount? Here it was 15. Now it is 10 plus 3, 13. So therefore, certainly this is smaller. If I remove at least from one box, some positive amount is removed, then certainly the total sum is right. And therefore, no matter if k square is equal to 2k square greater, doesn't matter. But the third box is smaller, certainly, and therefore the total sum is smaller. Is it clear now?
Yes, sir.
Yes, sir.
Okay, very good. So, therefore, 3 raised to k plus 1 is greater than k square plus 2k plus 1. But what is this? K plus 1 bracket square. And this we are doing for k greater equal to 2. We are not talking about 1, because for n is equal to 1 we have already verified. So we are not worried about k is equal to 1. Right? And therefore, this is what we were expecting. 3 raised to k plus 1 is greater than k plus 1 square. This is what our expectation was. Right? Hence, the result is true for n is equal to k plus 1. The result holds for n is equal to k plus 1. Right? Therefore, by induction, from k to k plus 1 we are able to prove. So by induction, 3 raised to n is greater than n square for all natural numbers. That is what are we were expecting. So now here we verified for n is equal to 1, but n is equal to 1 was of course the statement is true for n is equal to 1, but that was not sufficient as far as the our proof is concerned. We needed to verify for n is equal to 2, so we verified for n is equal to 2, because that was a requirement of this problem, right? And therefore your strategy depends on what is your problem, particular problem, right? It is not true that every time n is equal to 1 and then k plus 1. Sometimes you need to verify for 2, 3. It depends on the problem, and that power you should develop. You should be identify the problem. You should be able to analyze the problem, and then use the strategy. Right? Okay. So now we have some more generalization. So more generalization or general arbitrary base case. So arbitrary base case means sometimes we need the base case to be some higher, right? So arbitrary base case in induction. So arbitrary base case in induction means what? So what is the late is subset of n, and let us take n naught is some natural number, right? So assume that now n naught is a fixed, now it is a particular number. Assume that the n naught is member of set A, and K belongs to A implies K plus 1 belongs to A. Then, okay, now what is the situation? Situation is this is n naught, and n naught is a member of A, our set A. And if you choose any K from A, the next K plus 1 is also in A. Then what is the conclusion? Then what? Then the set n belongs to n such that n is greater equal this particular n naught is entirely contained in A. That means A contains all the natural numbers after n naught. A contains all the natural numbers. What is this set? N natural numbers which are greater equal n naught means all the natural numbers after n naught. Suppose n naught is equal to 10. Then A contains 11, 12, 13, 14, all. No
All
number is
after
missed.
10.
Right, so no number is missed out after 10th number, right? So that is what the meaning of this is. And here but we are not worried, we are not sure that the previous numbers like n naught minus 1 or 1 2 3 are members of A. That is not sure from this, and we are not interested in this case now. What we are sure, if our set satisfies these two properties, it contains some n naught, and if you choose any K after n naught, and then K plus 1 is also member of A, then the set A contains all the natural numbers after n naught. That is what the meaning of this statement is, right? And if you compare our the previous or first version of induction, what was n naught? So if n naught is equal to 1, then this is avatar 1 of induction principle. That is what we saw, right? This is what n naught is equal to 1, then we'll get the basic principle or avatar 1, and therefore this is the most general, right? So general version or general avatar of induction principle. If n naught is equal to 1, we'll get our original principle, and therefore it is true for you start with any n naught, the induction works. Is it clear? So
Yes, sir.
so steps, what are the steps to apply this general version? So steps to apply general version, and steps are exactly similar. So what is the first step? Prove that the statement is true for n is equal to n naught. Second step, induction hypothesis. What is induction hypothesis? Assume that the statement is true for n is equal to k greater equal n naught. In our original induction hypothesis, previous hypothesis was k greater equal 1, right? That was our assumption. So step 3, prove for n is equal to k plus 1, and therefore steps are exactly same. Only the difference is the base case is n is equal to not 1, n is equal to general n naught. Right, and then let us see some problem which needs this kind of induction, and then you can understand it better. So prove that. Prove that n factorial is greater than 2 raised to n for all natural numbers. For all natural numbers greater than or equal to 4. For natural numbers n greater equal 4. That means for n is equal to 3, this is not true. For n is equal to 2, for n is equal to 2, for example, what is 2 factorial is 2, and 2 raised to 2 is 4. In that case, for n is equal to 2, 2 factorial is 2, and 2 raised to 2 is 4. So not greater, right? This is not possible. Or n is equal to 3, then 3 factorial is 6, and 2 raised to 3 is 8. Not greater, right? So, but certainly for n is equal to 4, but n is equal to 1, 2, 3, it is not true. And it is true for n is equal to 4, and we want to prove that it is true for all n. That is what our claim is. Right. So what is step 1? Base case. So what is the base case? Prove for. Okay. So what is n naught in this case? N naught is equal to 4. Right. Prove for n is equal to n naught. Right. And n naught is in this case. But if n is equal to 4, what is n factor 4 factorial? It is 24.
24.
And, and it is greater than 2 raised to 4. 2 raised to 4 is 16. Right. Which is 2 raised to n in this, and therefore it is true for, clearly true for n is equal to 2. Assume that the statement hold for n is equal to k, and what is k is now greater than or equal to 4, not any arbitrary. So but k is arbitrary, but it is not less than 4, so it is greater than 4. That we should make, because base case is 4. That is k factorial is greater than 2 raised to k. This is our assumption. Now what is step 3? Now I will not write down all the details, but what is step 3? In step 3, what we want, right? What we want, the statement is true for n is equal to k plus 1. That means what we, k plus 1 factorial is greater than 2 raised to k plus 1. This is what we expect at this step. Okay, so consider k plus 1 factorial. Start with this and then try to achieve our goal, that it is greater than 2 raised to k plus 1. So k factorial is k plus 1 times k factorial, right? So this is correct. I can split k plus 1 factorial in this way. K plus 1 I am separating, and whatever remaining part is k factorial. Right. Correct. Okay. Now k factorial, I will replace k. I will compare k factorial and 2 raised to. Which is bigger? Forget about k plus 1. Just compare k factorial and 2 raised to k. Which is bigger? K factorial by induction hypothesis. Right. but I will multiply both sides by k plus 1. I will multiply both sides by k plus 1. So k plus 1 is positive amount. K plus 1 is positive amount. K factorial is greater than 2 raised to k, and I am multiplying both sides by some positive amount, and therefore inequality remains same, greater than. Correct? That means k plus 1 factorial. Basically, this is k plus 1 factorial, but I am just looking it into different way. So k plus 1 factorial is greater than 2 raised to k times k plus 1. Fine.
The screen is not visible.
Not visible.
Yes.
But some people can see the
It
screen,
is
right?
visible.
Yes, sir, it is visible.
Right.
Yes, sir.
Yes,
It's
sir.
visible.
So it happens due to internet connectivity. So don't get panic. So if internet speed downs, then it makes some. Okay, so okay, we are at this stage now. Now since about that, what is our k? K is greater or equal
So
to.
your voice is not coming.
Therefore, so k is greater or equal 4. Am I right? Because
Yes,
we are
sir.
not worried about smaller. So k is
Yes,
greater or
sir.
equal 4. And therefore k plus 1 is greater or equal 4 plus 1, which is what? Which is 5. And 5 is certainly greater than 2. Am I right? Our k, whatever k we are considering in these calculations, our k is certainly greater or equal 4. We are not talking about k smaller than 4. So of course our k is greater or equal 4. K plus 1 is greater than 4 plus 1. Right? And so k plus 1 is greater than 4 plus 1, which is 5. And certainly 5 is greater than 2. The transitivity, k plus 1 is greater than 2 because our k is greater equal 4. So am I right? Right. So therefore what should I write now? Therefore k plus 1 factorial, which was by previous calculations, it was greater than 2 raised to k times k plus 1. But now again we found that k plus 1 is now okay. Forget about previous part. So 2 raised to k I will keep as it is, and I will replace k plus 1 by 2. So this is k plus 1 and 2, and I know that k plus 1 is greater than 2. K plus 1 is greater than 2, and I am multiplying both sides by the positive amount, which is 2 raised to k, and therefore this quantity is right. K plus 1 is greater than 2, and I am multiplying both sides by 2 raised to k, and therefore the product again great, which is 2 raised to k plus 1. This is 2 means 2 raised to 1, and bases are same, therefore we can add exponents. So it is 2 raised to k plus 1. So ultimately what we get, k plus 1 factorial is strictly greater than 2 raised to k plus 1. Therefore the statement is true. Is true for n is equal to k plus 1, because now we can clearly see that the statement result holds for n is equal to k plus 1. Hence, by induction, the result is true for all n greater equal 4. Hence, uh, by induction, what? N factorial is greater than 2 raised to n for all n greater equal 4. Now we can declare, we are in a position to declare that it is true for all natural numbers greater than or equal to 4. Fine. Okay. So,
Sir,
yes,
sir, I have one question.
yes.
Sir, why have you written k plus 1 factorial is equals to k plus 1 into k factorial?
Is it wrong statement, first of all?
Sir, I have not understood why
But
you
you're
have written it, sir.
no, why I have written that is a later question. But the first question is it correct or not? This what k plus 1 factorial is same as k plus 1 into k factorial. Is it correct or not?
That I don't know, sir.
Yeah,
So it is correct.
right.
Yes, sir, this is correct.
Suppose
Yes,
5
sir, it is.
factorial is, okay, wait, 5 factorial is 5 into 4 into 3 into 2 into 1, right? Okay, 5. I will look at, I will separate these two parts. 5. What is the bracket now? 4 factorial,
Yes,
right?
understood, sir.
Factorial is 5 and 4 factorial. So I can write this. So your question is, see, why I have written in this way. So first of all, this is a first thing. Second thing, what is my aim? I want to achieve this. This is my goal. And if I want to achieve some goal, my goal is clear. I want to achieve this. Once your goal is using all the rules and regulation, you can achieve your goal. And that's why I'm using some rules and regulations. I'm not violating any rule. And my goal is, my target is this. To achieve the target, I am taking this kind of steps without violating any rule. Is it clear logically? What your question is correct logically. Why I'm doing this step? But my philosophy is I want to achieve this goal. And to achieve this goal, I am taking some modifications in my expressions. And while making this modification, I cannot violate any rule, right?
Okay,
Whatever
sir,
expression
understood.
I have written, right? That is what the logically means.
Sir,
Thank you, sir.
for that, for 2k, 2 raised to k plus 1, we can also write 2k and down at k plus 1.
Pardon? 2 raised to k plus 1.
For that, so we can write like that. You have written.
No. But we don't need that. Whatever needed, that we do. Suppose your goal is to pass some exam. What you will do? You will change your strategy. You will violate the law. You will not cheat in the exam. You will not do the cheating while writing. This is a violation of rule. But if you want to pass the exam, your goal is to pass the exam. What you will do? You will refer various books. You will solve some question papers, and then you will try to improve your knowledge, and you will do modification in your strategies. But you will not violate the rule, right? You will do all that is necessary. What I am doing, all that is necessary. I will not do unnecessary things. Why? Suppose you need this to pass the some mathematics exam, you will not read physics books, because reading physics books to pass maths exam is unnecessary thing. Is it clear? So logically, why you are thinking about unnecessary steps? Whatever necessary, that is what I am using. That will save my energy and time, right? Is it clear now?
Yes, sir.
Sir,
Yes,
can you
sir.
please repeat the step k plus 1 factorial greater than 2 to the power k into k plus 1 greater than 2 to the power k into 2? I didn't understand it.
K plus 1 factorial is greater than 2 to the power k plus 1. This step is clear.
Yes.
This step is clear. Now, what is the k plus? Now compare k plus 1 and 2. 2 to the power k. 2 to the power k is same. Now forget about 2 to the power k. Just compare k plus 1 and 2. Which is a bigger amount? Right? Which is a bigger amount? Just compare 2 to the okay. Just compare k and 2, which is a bigger. I have explained here, right?
K is bigger.
K is greater equal 4, so k plus 1 is greater than 4 plus 1, but 4 plus 1 is 5, and 5 is certainly greater than 2. Why I am taking 2?
Yes.
Why I did not take here 3? Because 3 is not useful for me. 2 is useful, right? So I am avoiding the, so 2 is useful. That's why I am taking 2 here. Otherwise 3 is also less than 5. 4 is also less than 5. 1 is also less than 5. But those numbers are not useful for me at this moment. Whatever is useful, I will pick that. So 5 is greater than 2, and I will pick that point. K plus 1 is bigger than 2. 2 raised to k, 2 raised to k is same thing. That doesn't matter. But if you compare these two terms, 2 raised to k is same. If you compare the second factor, then 2 is smaller. That is 2 raised to k plus 1.
Yes, I understood.
Right. So see, you should think about all such very simple steps. One can say these are silly steps or silly questions, but no question is a silly question in mathematics. Remember this, because there is a lots
Sir,
of
I have a
logic here.
doubt.
Yes.
Sir, if you want to compare k plus 1 is greater than 2k, and
Hmm.
if we put k as 4,
Hmm.
then k means 4 plus 1, that is 5, and 2 raised to 4, that is.
No. What is k? K is 4. What
Yes, sir.
part? Repeat your question. What you want to
Means,
compare?
see this, we have considered in step 3 that k plus 1
Uh,
is greater than 2k, 2 raised to 2 to the power k.
no. K plus 1 is greater than 2. That is what the I am saying. Okay, let me tell you again. 2 raised to k, 2 raised to k, no problem. Okay, now k plus 1 is greater than 2. This is true. This is true. K
Yes,
plus
sir.
1 is greater
Yes.
than 2.
Yes, sir.
Fine.
But
Now multiply both sides by 2 to the power k. 2 to the power k. And 2 to the power k is a positive number. And simply I am same property. A is greater than b and multiply by some positive number on both sides. Then inequality remains same. K plus 1 is greater than 2 and I am multiplying by c. C is 2 raised to the k on both sides. Then inequality, that is what I am using here. Is it clear now? Is it clear? 2 to k plus 1 is greater than 2. Multiply both sides by 2 to the power k, which is same amount, positive amount. So inequality is still greater because k plus 1 is greater than 2.
yes, sir.
Right.
Yes,
Okay.
sir.
Yes, sir.
Very. Now, in this induction, this is again for weak induction because base case could be any number, but it is exactly similar to the our previous version, right? Now, there is some more general version or strong version of second principle. Uh, Second principle of induction or strong induction. A strong induction. What is a strong induction? If you recall the weak induction, what was the weak induction? If A is a subset of natural numbers, 1 belongs to A and K belongs to A, implies K plus 1 belongs to A, then A is set of natural numbers. Right? This was our weak induction or weak principle or induction principle. So let, as compared to this weak induction, what is the difference between strong induction or second principle? So let A is a subset of natural number. Again, I am taking set of natural numbers. Suppose one is member of A, exactly same as this. One is a member of A, and what is the second property? If 1, 2, 3 up to K belongs to A, implies k plus 1 belongs to A. Right. That is 1, 2 up to k is subset of A. Then the next number, which is k plus 1, is also member of. Then is nothing but set of natural numbers. That means A contains all natural numbers. Okay, now compare weak induction and strong induction. What is the difference? Suppose A is a set of natural numbers, it contains first natural number, and in weak induction we were assuming that if it contains some k, natural number k, then it contains next also. In strong induction, what we are assuming? If our set contains all the natural numbers up to k, 1, 2, 3 up to k, all up to k, no number is missed out. If it contains all up to k, and from that if you are able to prove that it contains next k plus 1, then it contains all the natural numbers. That means A is equal to set of natural numbers. That is the difference, right? So I think there is no difficulty to understand this. If it contains first natural numbers, and if it contains all natural numbers up to k, and from that if we can able to prove that it contains, right, it implies that it contains next natural number k plus 1, then it contains all the natural numbers. That means it is exactly the set of natural numbers. So what are the steps to apply strong induction?
दोनों के बीच में अभी डिफरेंस नहीं समझ रहा है.
Yes.
Sir, it wasn't clear. What is the difference between this and the inductive property of natural numbers, or even that this and the weak induction?
Yeah, so in weak induction, see, I have written on the right side. What is our assumption? We are assuming only for k, and then from that we are whatever is about k minus 1, k minus 2 or previous numbers, right? But here we are assuming that it contains 1, 2, 3 up to k, all before k, and then from that you are proving for k plus 1. This is a difference. Is it clear?
Sure, sir. Even in weak induction, we say that 1, 2, 3 to, means like we just assume 1 and then directly assume it is equal to k.
Yeah, you are right, because we are assuming for arbitrary. From that we are proving here. See, logically, see, all weak induction, strong induction, inductive property, well ordering property, all are equivalent. Their meaning, logical meaning is same. But to understand logical meaning is same, we need to prove that these are equivalent, but that is difficult thing that we'll discuss later on. But in weak induction, we are assuming, we are not worried about, certainly we are proving for n is equal to 1, and we are assuming for k. From that k step, we are proving k plus 1, right? We are not considering k minus 1 at this moment. We fix some, see, we fix some k, whatever k you fix this k, and from that you are proving for k plus 1, right? We are not considering previous part at this. Happens to be true from k to k plus 1. By the logic, already it is true for 1, and by the logic for any k to k plus 1 it is true. By the logic from 1 to 2 it is true, 2 to 3 it is true, and it is true for all k. That is what the logic. But at this moment, while applying weak induction, we are not worried about k minus 1 and all this. But while applying strong induction, we are worried about k minus 1, k minus 2 up to 1. That is what the main difference is. Is it clear
Sir,
now?
then, but k is a variable. K can literally take any value from 2 to like literally any natural number. So what's the
K is variable, but at this moment, at this particular moment, we have fixed k, and from that k we are proving for k plus. When you are saying k is variable, then why to put k plus 1? Then it may vary to k plus 1 also. We understand. When you are saying k is variable, then why to prove for k plus 1? Then it will vary k plus 1, k plus 2, k plus 3. Right. So logically, we are at the moment we are fixing some k, and from that k we are proving for k plus 1. What k we are fixing, that doesn't matter. Suppose you fix 10, and from 10 can you prove for 11? Yes, certainly. But that is not sufficient, because from 10 to 11 is not sufficient. Can you prove from 12 to 30? Can you prove 100 to 101? So we cannot do this for each number. So we are assuming some general k. Choose any k, and we are at this moment we are fixing our k, and from that k we are proving for next, and then it works for all. That is the logic. That is a philosophy. So you need to understand. You think, when we apply induction, in induction hypothesis, we are assuming K, fixing something. We are not varying K at this moment. And from that K, we are proving for next. Whatever is K we have fixed, for next can you prove? That is the step. So therefore, we are fixing K, not variable K. At the moment, K is not variable. And now by logic, it is true for all. Is it clear now?
But sir, is there any a case in which the weak induction fails and we have to use strong induction for a better proof?
Weak induction, there is nothing weak induction fails. Weak induction cannot fail. We cannot apply weak induction. It is difficult to apply weak induction. That is the problem. Weak induction doesn't help. For example, if you want to go travel some 100 kilometers and use cycle, it doesn't mean cycle will fail. Certainly, you can travel by 100 kilometers by cycle, but cycle is not a convenient thing, right? You should use a car or motorbike. Am I right?
So, sir, what are such examples where we cannot apply weak induction but strong induction
Yeah,
can be applied?
that
Is more convenient.
for that you should wait. For that you should wait. I am telling the steps, and then certainly I will come to the problems. Correct?
Yes, yes, sir.
Okay, sir.
Right. So what are the steps to apply strong induction? So that is the difference between weak induction and strong induction. So you cannot use cycle always. Certainly you can travel 100 kilometers by cycle, but it is not convenient. It is very, so you should use the motorcycle or car. That is what the difference between strong induction and weak induction. So step one. Okay. So prove that the statement is true for n is equal to 1. Step 2. So please remind me if I am over time. I think it is 2 o'clock. So okay, I will just write down the steps.
Sir, sir,
Assume that, yes.
sir, please share this PDF on Teams.
Okay, assume that the statement is true for n is equal to 1, 2, 3 up to k. Right, now we are assuming that statement is true for all up to k. This is my induction hypothesis. And step 3, prove for n is equal to k plus 1. That is what the strong induction, how we apply. We prove for, assume for up to k, and then from that prove for k plus. Right, now you can understand. It is not difficult to understand the steps. Next time we'll see the problems where we can apply strong induction, and weak induction is not convenient in that case. So that we will discuss later on. So still any doubts, any difficulty?